All right, this is Dr. Bauer again. We're going to look at section 1.2 in Rosen's text. It's applications of propositional logic. Now, most of the applications of propositional logic require that you first translate some English sentences or a paragraph or an argument into logical symbolism. This process is helpful to clarify what is meant by each sentence, because when you have to translate it into logic, you have to make it more clear in the symbolism. So after the translation, then you can analyze the argument for validity. You can consider when it's true or not, or you can combine the logical propositions with other propositions. We're going to look at some examples that illustrate this. So first example is the English sentence, you can access the website only if you are over age 18. So what does this mean? Does it mean that if you are over age 18, then you can access the website? What does that phrase only if mean? I would say no, it doesn't mean if you are over 18, then you can access the website, because there may be some other requirements for accessing the website, such as a payment of some subscription for the website. Does it mean if you can access the website, then you must be over age 18? Okay, in order to help explain this, I just switched to the bottom of the first page of the notes for this week 1 notes. And if you recall, it says all of the following mean if P then Q, or P implies Q. P implies Q is the same as if P then Q. P is sufficient for Q. Q whenever P is true. Also P only if Q. So do you recall that P only if Q means if P then Q? Okay, so if we go back to the slides and look at this sentence, you can access the website only if you are over age 18. Then that would make sense that it would mean if you can access the website, then you must be over age 18. All right, so that's given in the notes, in the first page of the notes. That order, if P then Q, is going to stay the same as P only if Q. All right, let's look at another example. Write in symbols, to have a good day, all I need is a great attitude. So if you take that sentence, to have a good day, all I need is a great attitude, and you represent G to be have a good day, and the letter A to represent I have a good attitude, then this could be rephrased as G, I'll have a good day, whenever A, in other words, whenever I have a good attitude. Or A is sufficient for G. In other words, if I had, or it's sufficient for me to have a great attitude for G to be true, for me to have a good day. Now both of these can be written as A implies G, or if A, then G is true. If I have a great attitude, then I will have a good day. You can tell this sufficient aspect is implied in all I need is a great attitude. So having a great attitude is sufficient for having a good day. Okay, here's another example. Unless you read the manual carefully, you will not understand what to do. So if we let M equals you read the manual carefully, and U equals you will understand what to do. So the real question is, does the statement mean if you read the manual, then you'll understand what to do? Or does it mean something else? What does unless you read the manual carefully, you will not understand what to do. It does not mean if you read the manual, then you will understand what to do, because there might be some other reason why you don't understand what to do. But it instead means if you don't read the manual, then you will not understand what to do. It's almost like reading the manual is one necessary condition, but it's not necessarily the only condition, but it is a necessary condition. So if you don't read the manual, then you won't understand what to do, since it's referring to the condition when the person would not understand. So this statement, if or not am implies not you, really is equivalent to if you understand what to do, then you must have read the manual, using the contrapositive. See, the contrapositive would switch and negate. So if we have not am implies not you, you switch that and negate that, that would be you, then am. Okay, so this statement, unless you read the manual carefully, you will not understand what to do, could be summarized or written as an if-then statement in symbols: if you, then am. Okay, now looking at the example, those who have a passport visa or are a citizen of the country are those who can have access to the National Library. So if we let P equals have a passport visa, and then C equals are a citizen of the country, and NB have access to the National Library, then the statement says those who have a passport visa or are a citizen of the country. So we need to use the or symbol, the upside down V. So we have P or C, citizen, is equivalent to N. Now notice why I said is equivalent to N. The statement says those who have a passport visa or are a citizen of the country are those, are whose, it should read, are those who have access to the National Library. So we're equating the group of those who have the passport visa or are a citizen. We're equating that group with those who have access to the National Library. So that's why it's an equivalent statement. Now, equivalent statements are like the biconditional, because it goes both ways. So the symbolism would be P or C is equivalent to N. And if I wanted to write that as two statements, I could, using, directional arrows and having it switched around, because the biconditional statement can go both ways. All right. All right, some more examples. So if you have the statement, you must do your homework unless you ace the test or don't care about passing. How would we write that in symbols? So we're going to use the letter H for doing your homework. You must do your homework. The letter A. Something's happening with my video. Hello. Okay, so what I do on some of these situations is I first postulate on what does this mean? And I might be wrong. I might have it wrong, and so I have to rethink it and turn it around. Now, this statement is tied together. You must do your homework unless you ace the test or don't care about passing. That word unless is tying things together. So what does this mean? Now you can see that you have ace the test or don't care about passing. So that ace the test or don't care about passing is, tied together with a conjunction, an or situation. So I said, okay, does this mean, as you see right here, if you do your homework, then you either ace the test or don't care about passing. Is that what it means? No, that doesn't really make sense. Of course not, since doing homework would not necessarily mean that you either ace the test or don't care. So let's look at that P unless Q. Examine that. This means if Q is not true, then P is going to be true. See, it's saying P is true unless Q. But if Q is not true, then P is going to be true. I think this unless situation will make sense if you consider the statement, the plant dies unless it's watered. Now, obviously, that means if it's not watered, then it will die. So if not Q, then P. Now, since the contrapositive is equivalent to this, it also means if P is not true, then Q is true. See, we were taking if not Q, then P. The contrapositive of that means you're going to negate both and switch both. So it would be if P is not true, then Q is true. Thus, the statement can be written as if you do not do your homework, then either you ace the test or you don't care. All right? Now, that statement, if you do not do your homework, then you either ace the test or don't care, is equivalent to, if we wanted to negate both, if you don't ace the test and you care, then you must do your homework. But that is something we'll talk about why, when you negate that or situation, it becomes an and. We'll talk about that later. But anyway, it's called De Morgan's Law is what we're using there, but that's something we're going to talk about later. But both these statements do make sense when you translate them back into English sentences, okay? So sometimes it's a little tricky and you have to try it one way, and if it doesn't seem like it makes sense, try it the other way. Anyway, let's move on. All right, so system specifications are a set of statements that might be written in some manual about a program or a system. And to test whether the system specs are consistent, you just need to find a time when all the statements can be true. So it's a set of truth values for the propositions P and Q, or whatever the propositions are, that would make all those statements in the system specs true. So here's an example. The diagnostic message is stored in the buffer or it is retransmitted. The diagnostic message is not stored in the buffer. If the diagnostic message is stored in the buffer, then it is retransmitted. Now, I don't know why these statements would be in a system specifications situation, but let's just suppose they are. And we have to see if they're consistent. So to be consistent, to see if they are, we'll first translate them into symbolism. So we're going to let P represent the diagnostic message is stored in the buffer. Q represent the diagnostic message is retransmitted. So it really only has two statements. Now the first sentence, that the diagnostic message is stored in the buffer or it is retransmitted, would be represented by P or Q. So P upside down V, Q. The second statement says that the diagnostic message is not stored in the buffer. So that's just not P. The third message or statement is if the diagnostic message is stored in the buffer, then it is retransmitted. So that's P implies Q. Sorry, P implies Q. So those are the symbolic way to write those three statements. Now, an assignment of truth values that makes all of these true, it has to have P false, because when you have not P, to make not P true, we have to have P false. And then if P is false, and we have to have P or Q to be true, and P is false, then we have to have Q to be true. So what happens if P is false and Q is true to the third statement, which is the implication, if P then Q? Well, because P implies Q is true when P is false and Q is true, then we know that these specs are going to be consistent. All right, so all three statements are true if P is false, but Q is true. The first one, P or Q, would be true because Q is true. The second one, if P is false, not P is going to be true. And the third one, not if P is false, an if-then statement is true if the first part of it is false. So all three are consistent. We say the system specifications are consistent. They can all be true at the same time. And we could have also found this out by making a truth table. And if you can find one row of the truth table where all three of the statements are true, make a truth table where you have as your last three columns those three statements. If you can find a row where all three are true, then you have shown the system specifications are consistent. Now, logic in Boolean searches is just an application of these conjunctions or disjunction, the and or the or the not. And so when an internet search is conducted and you want to find car stereo systems, then you can use the search stereo and system. So it has to have both the stereo word and the system word and car or automobile, because it could be called either one. So your parentheses there are necessary because you want the or to be done first and then the and otherwise and would be done. And then if you want stereo speakers but not whole systems, you could say stereo and speaker, not system, and car or automobile. So here's a question: how would you search for suede or leather clothing but not belts? Well, you would just say suede or leather in parentheses and clothing, not belts. All right. In review, here's a few more last examples. If you had to translate the sentence, whenever I eat greasy food and then drive somewhere, I get sick. So do you see this is a if-then, because whenever implies, if something, then something else. But there's an and in there too. So if I was to write this, all right, so whenever, so that's like the if. So I'm going to put a parentheses and then an arrow, and I'm eating greasy food and driving somewhere, so I'm going to do an and. So the greasy food and driving somewhere, if those are both true, then I get sick. So that's how you could write it in symbols. Excuse my second grade writing there. Then here's another example. Are the following statements consistent? The code is either written incorrectly or the data is bad. If the data is bad, then the program will freeze up. The program did not freeze up, and I know the code is written correctly. So if all of those statements, or can all of those statements be true at the same time? So let's, first of all, let me erase this, and then we'll move to the next slide. So I've done it, I'm going to do it in a way that we're using the truth table. So the first statement are the code is either written incorrectly or the data is bad. So what would that statement be? Well, let me get my pen here. The code is either written incorrectly, so that's letter C in my system of symbols. So it'd be C, or the data is bad. I'm sorry, incorrectly. The code is either written incorrectly. And so it's going to be not C. Not C or D. The second statement, if the data is bad, then the program will freeze up. That would be if D, then, so you're going to put an arrow, freeze up, F. So that's the second statement. And the third statement, the program did not freeze up, so not F. And, so that's the upside down V, I know the code is written correctly. So that's C, code is written correctly. So those are my three statements that I have to show consistent. So the truth table for this, now remember when I said if you have two columns you would need 4 rows? Well, how many rows would you need if you have three variables, 3 propositions? Well, you're going to take 2 to the 3rd power, which of course equals 8. So we need 8 rows for this, and you see my 8 rows. Now half of those rows will make true, half of them false, and then you subdivide that that half, each of the lower half and the upper half, and have 2 true, 2 false, 2 true, 2 false, and then you just alternate for the 3rd column. And that gets all the different possible combinations of true and false for those 3 letters. Okay, so not C, we're going to write, okay, going to basically do the opposite of the whole first column. So it's basically 4 F's, and then we're going to have 4 T's. Okay, and then I'm also going to do not F. Now not F is going to be F, T, F, T, F, T, F, T. Okay, this would be easier if I was doing ones and zeros. But all right, so we've got the negations. I needed the negation of C and the negation of F because they're used in the statements. All right, so then not C or D. Now if I look at the 2nd and the 4th columns, that has the D and the not C. Or is true whenever at least one of them is true. So that's going to be true. In the 2nd row, that's going to be true. In the 3rd row, that's going to be false. In the 4th one, that's going to be false because both, here and here, they're false. In the 5th row, that's going to be true because at least one is true. And the next one is going to be true. And the next one's going to be true. And lastly, the next one is going to be true. All right. Now I do D implies F. Now the easiest thing when you have an implication is to determine when it's false first. It's false whenever it's true for the first thing, but false for the second thing. So we're going to look at the D and the F column, and in the 2nd row, it's going to be false because it's true for the first part, but false for the second one. But then it's not false again until the 6th row. It's going to be false there. But then the rest of the time, you don't have a T, then F, so it's going to be true. So I'm going to just put true for the rest of these. It's hard to write with this mouse. All right, then the last column is the not if and C. So I'm going to look at the first column, the C column, and the not if, and I'm only going to find it to be true if both of them are true. So the second row has both the first column and the 5th column true. The third does not. The 4th does. The 5th does not. The 6th does not have both of them true. The 7th does not have both of them true. And the last row does not have both of them true. Now, the question is there any row here where all the options, or all 3 of these last 3 columns, are true? Well, the first row, nope. Second row, nope. Third row, nope. 4th row, nope. 5th row, nope. If I look down here, there's not any row that all of them are true. So conclusion is not consistent. Not consistent. Okay, I'll just abbreviate it there. All right, so I hope that helps. And I'll leave this up for a moment, but that's sections 1.2, translating from English into logical symbolism, and then trying to put those statements together to see if they're consistent or not. Those are the 2 main things in the section. All right.